All right, good morning, everyone. Let's get started. So this is graph algorithms part 2, I guess. We're going to be talking about two very fundamental, important problems, the stable matching problem and the maximum matching problem. And basically, this is going to be the last lecture that's going to be exclusively about graphs. And then next week, basically, we're going to in some sense come back to computational complexity theory, talk about reductions, define the class NP, non-deterministic polynomial time, talk about P versus MP, MP hardness, and so on. But like graphs, like graph problems in computer science are basically everywhere. So in some sense, graphs are like a prerequisite to talking about the stuff that we're going to talk later. Okay, so let's, we're going to start with, as I said, we're going to do stable matching problem and maximum matching problem. And we're going to start with the stable matching problem. And let me motivate this by an example, okay? So most of you are freshmen, so you're not really thinking about jobs right now, I think. But you probably should be thinking about internships in the summer. You know, you shouldn't be just sleeping during the summer. You should be working a little bit. So you might be doing some research, looking into companies. Maybe you can do some internships. So let's say that's you, Bob. And you have some options. You've done some research. So you say, OK, maybe I can work in Microsoft. Or maybe Moogle, maybe Umbrella Corporation, or KLG, I don't know. And you've done your research, you have like a preference list. So you can order these companies and say, well, you know what? I like Moogle the best, and then afterwards I like Microsoft. And then if that doesn't happen, then I'll be OK with KLG. And my last option will be Umbrella Corporation. And of course, you're not like the only one looking for internships. So you have classmates that are also looking at internships. And they also have this kind of ranking they've made for these companies. And from the company's perspective, you know, they get your applications and they rank you guys, right? So they say, well, Microsoft says, I think Alice is better than Bob, Bob is better than Charlie, Charlie is better than David, and so on and so forth. And each company has its own ranking. Okay? So this is, of course, one particular example, like finding internship, but you can imagine this scenario being similar if, let's say, medical residents are trying to be matched with hospitals, or like students applying to colleges. And, you know, there are some other very natural examples where this kind of situation arises. Okay, so you have this situation. And let's say you get some pairing up. So Alice maybe goes to Microsoft, Charlie goes to Umbrella, whatever. Is there anything that can potentially go wrong when we do some kind of pairing up? Well, one thing that can go wrong is the following. Okay, so as I said, suppose Alice gets mapped to Microsoft, Charlie gets mapped to Umbrella. But suppose that if Alice actually prefers to work for Umbrella rather than Microsoft. That's like he prefers that better. And let's say Umbrella actually prefers Alice better than Charlie. Okay? If this kind of situation happens, we say this is like an unstable pair, Alice and Umbrella. They prefer each other rather than to their current, basically, partners. And you can say, well, this is not good because they might like do you know, backdoor deal after the fact, and you know, screw up everything. You know, all these matchings can go like go wrong. So we don't like this. We don't want this to happen. So we have a problem at hand. Okay, so this is basically now an algorithmic problem we can think about. So we have some students, we have some companies, we want to match them together, but at the same time, we don't want any unstable pairs. Okay? Right, so I'm gonna define it more precisely, the problem, but yeah. There are variations where it can be one-to-one or not one-to-one. Okay, so what are we going to do? The steps we're gonna follow right now is the following 4 steps. First thing we have to do is like formulate the problem precisely so that we can study it precisely. Then we're gonna ask, is there a trivial algorithm for this problem? And then as a good algorithm designer, we're always gonna ask, can we do better? Is there a better algorithm? And then we're gonna see that there is indeed a better algorithm, and then we're gonna analyze that algorithm. Okay, but the first step is like to formulate the problem. So let's formulate this. But when we're formulating, actually, we're gonna also look if we can sort of meaningfully simplify the problem as well, so that our lives gets a bit easier if possible. So the purpose of all this step is basically you want to get rid of all the distractions, identify the crux of the problem, and like basically get a clean mathematical model that we can reason about easily. Okay. And since this is a lecture on graphs, of course we're gonna model this with a graph. And in particular, the kind of graph we're gonna look at is going to be called a bipartite graph. Okay. So what's a bipartite graph? It's quite simple. It looks something like this. Okay, so there are like basically 2 disjoint sets of edges. Let's call vertices, call them x and y. And all the edges has to basically go from x to y. Okay, so a formal definition would be, you would say a graph G is bipartite if there exists some bipartition of the vertex set V into 2 sets x and y. And each edge in this graph must connect a vertex in x to a vertex in y. So in particular, if you say, okay, this is the bipartition that I'm looking at, you cannot have an edge like this shown there, like connecting 2 vertices, let's say in x, or an edge that connects 2 vertices in y. Now, when you're given a graph G, I don't know, with an adjacency list format or matrix format, you can ask, is this bipartite or not? Which means like you're asking, is there some bipartition x and y of the vertices such that I can basically draw it like this? And this is non-trivial, actually. Even for humans, like if I show you the picture of a graph and you look at it and I ask you, is this bipartite? You might have trouble detecting if it's bipartite or not. For example, let's do it. Here's a very simple one. So is this bipartite? So why is this not bipartite? Because like no matter how you partition, like every edge, every vertices, they're connected to each other, right? So no matter how you partition them, in one side of the partition, like there's going to be 2 vertices at least, right? And those 2 vertices are going to be connected because every vertex here, every pair of vertices here are connected. Okay, so that's definitely not bipartite. What about this one? So who thinks, no, this is not bipartite? Okay, who thinks, yes, this is bipartite? Okay, so it's about 50-50. So the answer is that it actually is bipartite because look at so in one partition, look at like the top left vertex and the bottom right vertex, the diagonal. Put that in one part, x, and the remaining top right and bottom left to the other part. And then you see like that works, okay? So they're like, oh, yes. Okay, so you see like it's not an easy thing to see immediately whether, even like with a simple graph like this, or is it bipartite or not. How about this one? No, why? Because, well, it has that triangle there, right? So we saw like triangle, you cannot really make it bipartite. And if you're graph contains a triangle, well, it's doomed. How about if I gave you something like this? This is a tree, right? So maybe I give you some arbitrary tree, and you can ask, is a tree bipartite or not? Okay, so actually it turns out that trees are bipartite graphs. So how do you actually determine whether a graph is bipartite or not? Is there like an algorithm for this? Well, okay, so I'm not going to tell you what the algorithm is, but you're going to figure it out in the homework. Right? It's a good problem. Sometimes we give the bipartition explicitly. Like we say, here's a graph G, and here's the bipartition X and Y, and the edge set E. Okay? And when the graph is given like that, so you immediately know it's bipartite. You don't have to go into the trouble of like determining whether it's bipartite or not. You don't have to find the bipartition that works or whatever. Okay, now with bipartite graphs, there's a very important notion called matching. Okay, so often we are interested in finding a matching in a bipartite graph. So what does a matching mean? So it means the following. It's basically a subset of the edges that do not share an endpoint, that do not share a vertex. Okay? Let me show you some examples. So this red edge by itself is a matching, trivially. It's a subset of the edges and doesn't share an endpoint with any other edge because there's no other edge. Okay, let's add another edge here. So the first edge and the second edge. This is also matching because these two edges do not share a vertex, an endpoint. Now if we did this, added another edge like that, now this is not a matching because the first two edges, they share a vertex on the right. Now this guy here that has three edges is a matching, and indeed it's called a maximum matching. So what's a maximum matching? It's a matching basically with the largest possible number of edges. So you look at all possible matchings that this graph might have, and you pick the one like basically with the most number of edges. That's a maximum matching. And here you can see, so wow, can someone tell me why in this graph the maximum matching has to be 3? It cannot be more than 3?
Well, to answer that question, because Y only has 3 elements.
Right.
3 vertexes.
Yeah.
So if you had more, then one would go to 2.
Exactly. Just because Y has 3, the maximum matching must be at most 3. Yeah.
Is a maximum matching the largest number of edges? Like, is it the largest matching with the given vertices that you start with, or the largest matching assuming you can draw whatever edges you want?
No, so you're given a graph, it's fixed, and within that graph, you're asked, what's the maximum matching, right? Because like if, yeah, basically that's the problem. Okay, and there's another like related notion called a maximal matching, and a maximal matching is basically a matching which cannot contain any more edges. Like this example is actually a maximal matching because if I try to add any other edge to this matching, it will no longer be a matching. Okay, so you can check it. If I try to add any other edge, it's not going to be a matching anymore. So it's like maximal in that sense. So you can think of it as like it's a local kind of optimum. Okay, and it's not a maximal matching is not necessarily a maximum matching, right? So we saw in this graph we can get a bigger matching, a matching of size 3, but this is a maximal matching of size 2. And then there is what we call a perfect matching. It's a matching basically that covers all the vertices. Okay, So now I changed the graph a little bit so that each x and y has 4 vertices. And I'm showing you a matching here with 4 edges, and it touches every vertex. It's a perfect matching. And you can see that I had to add a vertex to y to do this, because a necessary condition for perfect matching is that the 2 sides, x and y, have the same number of vertices. Okay? Because otherwise I cannot match them up. A perfect matching, basically, you can also think of it as like a bijection between x and y. Okay. So bipartite graphs are like extremely important types of graphs. They model like various kinds of different situations really well. Examples, let's say the set X denotes some machines. Set Y denotes some jobs that those machines may or may not be able to do. And you say, and you put an edge between X and Y, a machine X and a job Y, if X is capable of doing that job Y. Okay, and then you might ask, now I want a matching, let's say, that covers every job, every vertex in Y. Okay, so you might ask a question like this. Like one specific example, if you think the machines as like professors and like the jobs being courses, and you put an edge between a professor and a course, meaning like this professor X can teach course Y, and then the department has to find like some matching that covers basically every course, hopefully. Okay. And like going back to our example, you can say X is the set of students, Y is the set of internship jobs, and you put an edge between X and Y, meaning X and Y are interested in each other. Okay? And you might want to find a matching there. Okay, so now let's go back to the internship problem again and try to formalize the problem in terms of graphs and matchings. Okay. So we can say that, and while we're doing this actually, I'm going to also at the same time simplify the problem a little bit, make some simplification assumptions, and that's all right. There are various versions of the problem you can study. This version that I'm going to describe to you will already be quite interesting to study. So we can say an instance of the problem can be represented as a complete bipartite graph. Complete bipartite graph. So what does that complete mean there? So it basically means you have X and Y, and you put all possible edges between the two. So the X represents the students, the Y represents the companies. We're going to assume, again, like a simplifying assumption in some sense, that X and Y have the same size. Let's call it N. And we're going to put all possible edges, meaning that, you know, every student is basically interested in every company, and every company is interested in every student, potentially. Okay, but that's not all we have in the problem. So we also have another thing, which is the preference list for each node in this graph, right? So we add that in as a list. We say, okay, the student A prefers the company E over F, prefers F over H, and H over G. And we have such a list basically for each node in the graph. And our goal now is to find a stable matching in this graph. Okay? So what is a stable matching? Okay? So let's simplify sort of the example here. Let's say we have two people, A and B, two companies, E and F, and the students basically both agree that, you know, company E is better than company F. And actually the companies also agree on the fact that the student A is better than student B. Okay, so they're in total agreement, fine. And then this is like this match, the red edges actually represent a stable matching. But what does stable matching mean? So the first thing is that it has to be a perfect matching. Okay, everyone has to be matched. And the second condition is that it cannot contain an unstable pair. So we sort of talked about unstable pairs. So what's an unstable pair? So a pair of vertices U and V are unstable, okay, if they prefer each other rather than to their current partners, over their current partners, okay? For example, okay, so that's basically what I said here, a pair of vertices U and V which are not matched to each other, but they prefer each other over their current partners. So this is a stable matching, but if I change the matching like this now, so that's a matching, but there is an unstable pair here. So what's an unstable pair here? A and E, right? So if you look at A and E, you can see that A prefers E over F, and clearly E also prefers A over B, right? So A and E prefer each other over their current partners. That's unstable. They might do a backdoor deal after the fact and screw things up, so we don't like that. So stable matching is a matching which is perfect matching, and it contains no unstable pair. Every pair is stable. Okay? All right. So this is our problem. This is how it looks like. Our goal is to find a stable matching. Now the first question that you might ask about this problem is, well, is there actually always a stable matching? Like you're given such an instance to the problem, are you guaranteed that there is going to be actually a stable matching or not? And that's like a highly non-trivial question, right? So there's no like trivial answer that you can say immediately, well, yes, there is always one, or maybe not. Okay, so we're gonna answer that question, but let's go to now second step, step 2, which is there some algorithm, some trivial algorithm that solves this? So what would be some algorithm? You know, you're not worried about time complexity at all. You just want something. What would you do?
Try all perfect matches and then check stop waiting to find one that's stable.
Exactly. So you try basically all perfect matchings, and then you check if that perfect matching is stable or not. If you find a stable perfect matching, you're done. Okay, and that's exactly what's written here. Question?
I was just going to suggest that in this special case where every element of Y has the same preference list, you can just give A what he wants, then give B what he wants. If A has different array, then give C what he wants, and give B what he wants. As long as like.
Right. So I mean, there might be special cases that you can handle more cleverly, but in arbitrary preference lists like that's not gonna really work. Okay, so if we do this though, let's just count how many perfect matchings are there. How many? 24? Well, I mean in general, when they're like n vertices and n vertices. Yeah. N factorial? Yeah, so that's right, because why is it n factorial?
A can go to 4 things, well, n0 can go to n
Right.
things, and n1 can go to n1.
Right. So yeah, we are looking at number of bijections basically, or a bijection is like a permutation, and the number of permutations of a set X is n factorial, where n is the size of X. Good. So yes, question.
What about the case where what about the case that one thing that access to be matched to Carnage each set are equal?
Right. So we're assuming that. So simplifying assumption, the sets have equal size. Okay, yeah. But like that's another problem. We can also study that, and yeah, then that would be different. It wouldn't be n factorial. But yeah, let's just assume that we want the size of X is the size of Y, and we want a perfect matching. Okay. Can we do better, right? So that's what we have to ask. Question? So the number of perfect matchings is n factorial. Right, so let's say I map A to some element, E, F, G, or H. But once I mapped A to some element, B cannot be matched to that element that A is matched to. So now B has one less option. Okay, and then C will have one less option and so on. So A has n options to go to. B is going to have n minus 1 options because it cannot be matched to where A is matched to, right? And then C is going to have n minus 2 options and so on. So that's why it's n times n minus 1 times n minus 2 times. It should cover all vertices, but they cannot, it's a matching, right? So they cannot share an endpoint. So basically, as I said, a perfect matching is like a bijection between x and y.
How do you check the matching table?
So you have to go through each,
Okay, other than that, okay.
right,
So that's
yeah, yeah. We're doing just the most obvious thing, yeah. But it's already like, even like checking stability was like constant time. Even in that case, it's a horrible algorithm because you have to do n factorial checks. So we definitely want something better. And we are going to do something better. And we're going to see an algorithm called the Gale-Shapley proposal algorithm. This is from 1962, actually. On the left, we have Gale. On the right, we have Shapley. And in fact, in 2012, Shapley won the Nobel Prize in economics, mostly for, this algorithm and some other work. So you say, well, what about the other guy? Well, actually, he passed away in like, I think 2008. But like, if he was alive, he would also have gotten it. Okay. So these guys are our heroes, I guess, for this lecture. And we're going to look at the algorithm, which is extremely elegant, like very nice algorithm. It's very easy to understand. And then we're going to actually prove that the algorithm works correctly. And the proof of correctness of the algorithm is also super elegant. All right, so it's very nice. So we're going to now see this algorithm. But let me just say, so the way we're going to now, I'm going to describe the algorithm is going to be as follows. So I'm going to sort of change the meaning of the sets. So we were thinking of the sets as students and internships. Now we're going to think of the set X as men, some set of men. And we're going to think of the set Y as some set of women. And we're trying to get them married. Okay. And the way it's going to work is men are just going to propose to the woman they like. And the women are like going to be okay or no, I don't like you. So they're going to either accept the proposal or reject the proposal depending on their preference list. And so on. Okay. Now you might ask, well, why are men proposing? Why are women proposing? You might say, well, why are there two sexes? Why can't two men get married and so on? So I'm not here specifically endorsing any views on marriage here in this lecture, okay? So this algorithm is just for illustration purposes, okay? So just keep that in mind. So, okay? So, all right. So I'm just going to, before like writing even down the algorithm in words, I'm just going to run the algorithm for you with an example. And like you're just going to understand how it works. And then afterwards, I'm going to actually write the algorithm too. Okay, so our first character is, who is this guy? Billy Bob. Yeah. Okay, so we have Billy Bob. So since we have Billy Bob, we're going to put Angelina Jolie there because at some point they were married. And since we have Angelina Jolie, we're going to have Brad Pitt. And since we have Brad Pitt, we're going to have Jennifer Aniston. And since we have Jennifer Aniston, we're going to put John Mayer into the mix. And for no particular reason, just for fun, we're going to add also Kim Kardashian. Okay, and then these people, they're going to have some preference lists. Okay, and and if you look, so the guys agree, like, right, Kim Kardashian is the way to go. And then they're like Jennifer Aniston, and then Angelina Jolie. But the girls, they have like mixed feelings, okay? So their first choice are different, actually. Okay, so here's the way the algorithm. So this is the instance, an instance of the problem. And we're going to now run the algorithm on this. The algorithm, the way it's going to go is, it just randomly, well, arbitrarily, let's say, picks some guy that's not matched. So let's say John Mayer. He's not currently matched. And then John Mayer is going to go to the first woman in his list, Kim Kardashian, and he's going to propose to Kim Kardashian. And Kim Kardashian is like, okay, well, you know, I'm not crazy about John Mayer. He's like on the last in my list, but I prefer being, so women prefer being matched rather than being single. So she actually accepts. Says, fine, you know, for the time being. She's like, she says yes, but in her head, she's like, no, if a better offer comes, like, I'm going to dump this, you know. All right, so they get matched. And then John Mayer says, okay, I crosses Kim Kardashian off his list, and they're matched for the time being. And then now, that's like one iteration of the algorithm. So now we go to the second iteration of the algorithm. And we just repeat this process. Like we say, okay, just pick an arbitrarily some guy who's not currently matched. So let's say we pick Brad Pitt. Brad Pitt will now say, okay, my first choice is Kim Kardashian. So I'm going to propose to Kim Kardashian. I don't care about John Mayer. And he does. He proposes. And then Kim Kardashian is like, yay. So she actually dumps John Mayer and says, okay, I'm going to be matched with you, Brad. And Brad is happy, and he crosses Kim Kardashian off his list. And then that's the second iteration. Now the third iteration, again, we pick just some guy that's not matched. So John Mayer was matched, but he's no longer matched, right? So we can pick him again and say, okay, now John Mayer goes to his second preference, Jennifer Aniston, proposes to her. Jennifer is like super happy because, I mean, it's her first choice. So they get matched. And then now we have John Mayer matched, Brad Pitt matched. So the algorithm is going to pick the next unmatched one person, Billy Bob. So we go to him. So he's like, okay, I'm going to propose to Kim Kardashian. I don't care about Brad Pitt. And then Kim Kardashian is like, I'm on a roll here. So she accepts Billy Bob because she prefers Billy Bob. And then they get matched. And then now Brad Pitt is unmatched. So we pick him. He first proposes to Jennifer Aniston because that's the next person in his list. But Jennifer is like, so up to this point, the woman just accepted all the proposals, basically. But now it's the first time, like, Jennifer's like, you know what, I'm happy with my matching. I don't want you. So she rejects Brad Pitt. And then Brad Pitt is kind of unhappy. So he crosses Jennifer from his list. And then there is, again, only one, still Brad Pitt left unmatched. He proposes to the person left, Angelina Jolie, and Angelina is super happy because it's her first choice. So they get matched, and we're done. Everyone is matched. When everyone is matched, the algorithm stops. Okay, so that's the algorithm. And like, if you were to write it down, you could write it down like informally like this. You could say, while there is a man who's not matched, we're going to repeat the following process. We're going to pick some M, a man M that's not matched. we're gonna let W be the highest ranked woman in M's list, to whom M has not proposed yet, right? So the highest ranked woman that's not crossed off in his list at that point. And then we check if W is unmatched, she's gonna accept, they're gonna get matched. Or if the woman W prefers actually M over her current partner, then again, she's gonna dump her current partner, and M and W are going to be matched. Okay, so that's it. So you say, yo, that's a pretty cool algorithm, but does it work? Like, it's not at all clear that this works or not. The first thing you can ask is, well, does it always actually terminate? Maybe it doesn't. Maybe you get stuck in some loop where, like, you know, people are just like proposing and rejecting and proposing and rejecting. And another thing is, does it always find a stable matching? Okay, you can sort of say, okay, maybe it finds a matching, but does it always find a stable matching? So why is this stable? And again, like, you can also, as we asked before, does a stable matching always exist in the first place? We don't know that. Okay, so let's now analyze the algorithm and see that it gives us the correct answer always. Okay, so here's the theorem. The Gale-Shapley proposal algorithm always terminates with a stable matching after at most n squared iterations. So iterations meaning like the number of times the outer while loop is going to repeat. It's going to repeat at most n squared times. Now this is quite remarkable actually. First of all, it tells us that every instance has a stable matching actually. And it gives us a constructive proof that there is a stable matching. It actually gives us one stable matching. And as I said, this is actually a highly non-trivial fact by itself, that whether there is a stable matching always or not. Okay, so now to prove this theorem, we need to do three things, okay? The first thing we're going to do is we're going to show that the number of iterations is at most n squared. And all of these are going to be pretty straightforward actually, but yeah. So the first thing is number of iterations at most n squared. The second thing we have to prove is basically that the matching we get is stable. But what's the definition of being stable? First, it has to be a perfect matching. So we're going to see that first it has to terminate with a perfect matching. And then the second part of the definition of a stable matching is that it should not contain any unstable pairs. There should not be any pair of a guy and a girl who prefer each other rather than over their current partners. Okay, so we're going to show these three things, and that will be enough to prove the whole theorem. Okay, so let's do number one. First of all, observe that the number of iterations in this algorithm is just the number of proposals. One iteration is one proposal. Okay, we're just going over proposal after proposal. Now, how many? So we want to count the number of proposals being done in this algorithm. So observe that no man proposes to a woman more than once. Okay, if I propose to a woman, if she rejects me, I cross her off my list, and I will never propose to that woman again. So each man makes at most n proposals, and we have in total n men. So n proposals per n men, n squared proposals in total at most, and the number of iterations at most n squared. Easy, okay? So that's nice. So it does not go into an infinite loop. The algorithm terminates, the second part is the algorithm terminates with a perfect matching. Okay, so to prove this, we're going to go by contradiction. So we're going to say, suppose it does not terminate with a perfect matching. And let's see what kind of contradiction we might get. So what does it mean if it's not a perfect matching? It means that some man is not matched to any woman. Right? There's some man who's not matched to any woman. What does that mean? Well, it means that this man got rejected basically by all the women. Okay, so probably he's not going to win the Sexiest Man Alive award. But yeah, there's this man who basically got rejected by all the women because if when a man is not matched, the algorithm picks a man that's not matched, and that man is going to has to go through all the proposals he has to go through, and then at the end, if he's not matched, he's not matched. But yeah, so this man got rejected by all the women, but now that means okay, that implies that all the women are engaged when the man proposes to them. Okay, so if I'm this man who's getting rejected all the time, so when I propose to a woman, either I'm going to be rejected by that woman because that woman is already matched, or that woman is not matched, then okay, she's going to be matched with me. But at that point, she's going to be engaged to me, right? She's going to be matched to me. So if I am rejected by all the women, then at some point in the algorithm, every woman has been engaged to someone. Okay. But also another observation is that if a woman is engaged, she stays engaged. She never goes from being engaged to being single. Okay. If she's engaged, she's going to stay engaged. She might change partners if someone better comes along, but she never prefers being single over being not single. Well, what does that mean then? All the women at some point in the algorithm are getting engaged, and when they're engaged, they stay engaged. So all the women are engaged. But if all the women are engaged at the end of the algorithm, well, how can that happen? That means all the men have to be engaged because women are matched perfectly with men. Okay, so and that's the contradiction we get, because what happened here? So we said a man is not engaged. That implies that all women must be engaged at some point in the algorithm. And if they're engaged at some point in the algorithm, they're engaged at the end of the algorithm. So all women are engaged at the end of the algorithm. That means all men are engaged at the end of the algorithm because they have to be matched together. And that's a contradiction. A man is not engaged implies all men are engaged. And then number 3, the matching has no unstable pairs. We have to show this. Okay, let me just again remind you, a pair of vertices are not is an unstable pair if they prefer each other over their current partners. So here's a very important observation to make. When you run this algorithm, Gale-Shapley algorithm, you see that a man can only go down in his preference list. He starts with the first woman in his preference list, and as he's proposing to woman, he goes down in his preference list. On the other hand, if you look at the woman, they only go up in their preference list, right? They accept someone's offer, and then they will dump that person for a better person, but they will never go down, right? They will never accept a proposal that is worse.
It might have just been the example that we did, but does this algorithm always work in the women's favor? Because they all got their first choice.
We're going to talk about this. Yeah, we're going to talk about this. But yeah, let's just complete this proof now. So this is an observation. That's a nice observation to make. Now, let's look at any pair M and W, and we're going to show that it must be stable. Okay, so it might be the case that after the algorithm runs, maybe M is matched to W prime, and W is maybe matched to M prime. And now we're looking at this pair MW, and we want to see, is this an unstable pair or not? Would they prefer each other over their current partners? Now there are two cases here. Okay, the first case is M never proposed to W in the first place, and case 2 is M did propose to W. So let's see what happens in each case. What happens if M never proposed to W? And just keep in mind that M can only go down in his preference list as he's proposing.
prime to W.
Exactly. So W prime must be higher in his preference list of M than W, right? Because if M never proposes to W and M is going down on his preference list, it must be that W prime is higher in his list, because if it was not, we would get a contradiction. And then case 2, you say, well, what if M does propose to W? What does that mean? Right, so and remember that a woman can only go up in her preference list. Well, that means W rejected M. M proposed, but W rejected because they're not matched. And why would she reject? If she gets a better offer, right? So W prefers her current partner, right? So you see in case 1, like M prefers his current partner. In case 2, W prefers her current partner. So this is definitely not unstable. So this is stable. Okay? And that's like 1, 2, 3, we're done. Okay, so further questions. So this is coming to what you ask, actually. So what other kinds of observations can we make about this algorithm? Okay, so we can ask, for example, does the order of the men we pick make a difference? So we arbitrarily pick an unmatched man and make him do a proposal. Does the order, if we pick a different order, would that lead to a different stable matching? And we can also ask, does this algorithm in some way favor man or woman or neither, or is it neutral? So maybe it's biased towards men in the sense that men get to be matched with like their higher preferences, or maybe it's biased more towards women where women get matched with their higher preferences, or maybe it's neutral, like there's no way to say the algorithm favors one or the other. So who thinks this algorithm favors men? Okay. Who thinks this algorithm favors women? Okay. Who thinks it's neither? Neutral. Okay, so that's pretty evenly divided. Okay, so let's see the answer to these questions. Okay. So to answer these questions, we're going to make a couple of definitions. So we're going to make the following definition of a valid partner. So we're going to say that W, a woman W, is a valid partner of a man M if there's some stable matching in which M and W are matched. Some stable matching. It doesn't have to be the matching that the algorithm returns. Just look at all possible stable matchings that might exist. If in one of them they are matched, M and W, then W is a valid partner of M. And we're going to say W is the best valid partner of M if W is the highest ranked woman in M's list among the valid partners. So I'm looking at all possible stable matchings, and I look at which woman M is matched to, and I pick the woman that has the highest rank among that. So that's the best valid partner, basically, that M can hope for. Here's the theorem. The Gale-Shapley algorithm always matches M with its best valid partner. Okay, so another way to say this is like you can say, let's define best of M to be the best valid partner of M. The Gale-Shapley algorithm basically returns you this matching, M comma best M, where M is in X. Now this is, in itself, is quite surprising actually, because it's not even clear that this set would be a matching. Like, why wouldn't two men have the same best valid partner? right? So like a priori, like, I don't know, you could say they could have the same best valid partner. And if that's the case, this wouldn't be a matching even. But basically this theorem is telling us that not only is it a matching, it's like a stable matching. So that's like quite surprising and interesting. So let's actually see the proof of this. Proof of man optimality of the Gale-Shapley algorithm. So suppose in the Gale-Shapley algorithm, there is some man not matched to his best valid partner, right? So again, we're going by contradiction. So suppose some man is not matched to his best valid partner. So that means that some man got rejected by his best valid partner. But actually, it also means like you can sort of weaken that and say some man got basically rejected by some valid partner in this algorithm, right? So because a best valid partner is a valid partner also. So some man got rejected by some valid partner during this algorithm. And what we're going to do is we're going to look at the first time that this happens in the algorithm. Okay? Consider the first time this happens in the algorithm, that a man gets rejected by some valid partner. So let's say that man is M, gets rejected by a valid partner W. So something like this. So during the Gale-Shapley algorithm, M basically, well, there are two ways this could happen, okay? So the first case is that M and W are matched, okay? During the algorithm, they get matched. But then W gets a better offer and then dumps M. So that's one case. The other case is W is already matched with a better partner M prime, and M like proposes, but like W says, I'm sorry, I'm already matched with a better partner. Okay, so we look at the snapshot when like the first time M is rejected by W, and at that point we know that W is now going to be matched with some M prime. Okay, and we know for sure that in W's preference list M prime is higher than M. Okay, so this is like right after M got rejected by W. So at the end of the algorithm, I'm not claiming that W and M prime are going to be end up together. So W might reject M prime too later. But this is like the first time this happens. Okay, so that's that. Now we know W is a valid partner of M. But what does it mean to be a valid partner? It means that there's some stable matching in which M and W are matched indeed. So let's look at that matching now. So there's some other stable matching where M and W are matched. Okay, so let's say it looks something like this, M and W. And in this matching, while M prime, this M prime from there, is going to be matched to some other woman. We don't know. Let's call it W prime. Okay. Now here's the thing. So let's add W prime to that picture as well. Okay. Now here's the thing. We assumed that this is the first time a man got rejected by a woman W. So it means that M prime could not have been rejected by W prime at this particular moment. Right? Because if M prime was rejected by W prime, then that would be the first time that a man got rejected by a woman. But we're saying M was the first time that got rejected. Okay? Okay? So M prime could not have been rejected by W prime. And what does that mean? Well, it means that W is higher in M prime's list. Right? Because men go down their preference list as they're proposing. Okay? So at some point, M prime proposed to W, and he has not yet proposed to W prime. So, Okay, W prefers W prime, W prefers W prime. But now is the contradiction, because now if we come back to this matching here and look at this pair, M prime and W, that's going to be an unstable pair. Okay, why? Because you see M prime prefers W over his current partner, W prime, and you look at W, well, she prefers M prime over her current partner, M. Unstable pair, and that's a contradiction, because we assume that this is some other stable matching. It cannot contain an unstable pair. And that completes the proof. Okay, now we can also sort of look at this from the woman's perspective. So let's again define this valid partner, best valid partner from the woman's perspective. It's the same definition, but we're flipping the M and the W. So M is a valid partner of W if there's some stable matching in which M and W are matched. M is the best valid partner of W if M is the highest ranked valid partner of W. And then, well, unfortunately, I will have to also make the following definition. M is the worst valid partner of W if M is the lowest rank valid partner of W. And now you can sort of guess, I guess, where this is going. So it's a theorem. The Gale-Shapley algorithm always matches W with its worst valid partner. Okay? Unfortunately. You have like different variations of this algorithm. So you have the original finding internship problem. You can say like, what if the woman can accept more than one proposal? Like, what if the companies can accept more than one student or application? You can look at the original finding internship problem with couples. So couples basically apply to the same residency or same company or whatever. You can look at like a stable roommate problem where you don't have explicitly like two sets, X and Y. There's just like everyone is one big pool, and you're trying to like match them together. Like maybe they're trying to find roommates or group members to work on a homework problem. And so there are various variations to this, and you can study these things as well. Okay, so now I'm going to move on to, yeah. People have solved these problems, yeah. These problems are studied. But some of them are like, when you add like couples, they can become actually NP hard, if you know what that means. So they can be computationally hard. So not all of these variations have an efficient algorithm necessarily. Okay, so now let's look at another problem. Well, we've been sort of looking at this, kind of define this as well, maximum matching. And it's another like fundamental problem. In some sense, it's more fundamental even than the stable matching problem. So as we said, a matching is a subset of the edges that do not share an endpoint. A maximum matching is like the maximum matching with maximum number of edges. Looks something like this. Okay. So you can also ask, by the way, I mean, we've been considering bipartite graphs, but you can also ask, can I find a maximum matching? I mean, you can define a notion of matching in an arbitrary graph. It doesn't have to be a bipartite graph, because matching is just a subset of the edges that do not share an endpoint. Okay, so you don't have to restrict yourself to bipartite graphs there. You can ask it for any kind of graph. And there are some natural matching, like very fundamental problems, like given a graph, find the maximum matching. Given a graph, does it have a perfect matching? If there is one, can you give me the perfect matching? And so on. And so perfect matching touches every vertex, as you can recall. So, you know, very interesting fundamental problems. And even when you restrict G to be bipartite, these are already quite interesting problems. Okay, so let's look at the following problem now. So you're given a bipartite graph with an explicit bipartition, and you want to find the maximum matching in G. So is there an algorithm that solves this? Try everything, right? Try all possible subsets of the edges. Check if it's a matching. Keep track of the maximum one found. So it's decidable at least. We know that. But again, it's exponential time. It's not good. So can we do better? The first thing you can try to do is just go greedily. So you can try sort of like a greedy algorithm, which means that, okay, you start with the first vertex on the left. You pick an edge. There you go. And then you say, okay, I'm going to put in my matching. And then you go now to the second vertex on the left. You pick an edge so that, it's still a matching. So you cannot pick the first edge. That wouldn't be a matching. But you can pick the second edge, and that would be a matching. That's fine. And then you say, okay, go to the third vertex, pick the edge. Okay, it's still a matching. But then you go to the fourth vertex. You cannot pick that edge, so you're done. So this way, you can get a maximal matching, but not necessarily a maximum matching, because actually, this particular graph, has actually a perfect matching with 4 edges. But the way we did it, we were able to just go up to 3. But then you can ask, okay, is there a way to get out of this local optimum? Okay, so this is like local optimum. Is there a way to get around it? Okay? And there is a way to get around it, and it uses this notion, a notion that's called augmenting path. So what's an augmenting path? So if M is some matching, an augmenting path with respect to M is a path in the graph G that satisfies 2 things. The first is that the edges in the path alternate between being in the matching and not being in the matching. Being in the matching, not being in the matching. And the second thing is that the first and the last vertices in this path are not going to be matched by M. They're not going to be incident to edge in the matching M. So basically it looks like this. Okay? So the red edges are the edges in the matching M. So you have an unmatched edge, matched edge, unmatched edge, and so on. And these vertices at the end, they're not matched, which means that this is not like next to any red edge. And same for the last one. Here's an example, like the same example. So we had this maximal matching, right? So these 3 edges. Now, I claim that the following is an augmenting path in this graph. The path that goes from 4, 8, 2, 5, 1, 7. Okay, if you stretch this out, it would look like this. 4, 8, 2, 5, 1, 7. Now suppose I find an augmenting path, like the one I just found here in this graph. What can I do? Someone who doesn't know the answer. Yeah.
You just flip.
Flip, right? So you say, okay, I am going to switch the matched and the unmatched edges, just like this. Now these are going to be the match ones, and the previous match ones are not going to be in my matching. And now it's nice because you got a matching which has one more edge in it, right? So an augmenting path basically implied that we could actually obtain a bigger matching. And this is a valid matching because, as you recall, by the definition of an augmenting path, this vertex was not like next to another red edge, right? And similarly for that one. So this is totally valid. Okay, so that's nice. So we say augmenting path implies that you can obtain a bigger matching. But what is like much better than that is the following. In fact, if there's no augmenting path in your graph with respect to the matching you found, then that matching is actually maximum matching. That's surprising. Like, why would you expect that? But it's true. So you can summarize this in this following theorem. You can say a matching M is maximum if and only if there's no augmenting path with respect to that matching. Okay, so I mean, I'm going to show you the proof of this, but like, suppose this is true, right? Then what would be like an algorithm to find the maximum matching? Okay.
So every time you find an augmented path, then you put the edges until you find it.
Yeah, I mean, you can start with basically one edge. That's a matching. Find an augmenting path with respect to that matching. Augment it, make it bigger. And then you have a new matching. Then find another augmenting path with respect to now that matching. Augment it, make it bigger, and so on, until you cannot find any augmenting paths anymore. And the theorem says that once you cannot find an augmenting path, well, you're done, because that has to be a maximum matching. Of course, there's the issue, how do you find an augmenting path? But if we just, for now, assume that you could do that efficiently, then this would be an efficient algorithm. Okay, so let's prove this then. Seems very useful. So, I mean, we've already seen this. This is like one direction is pretty trivial. So if there is an augmenting path with respect to M, we saw that M is not maximum because we can make it bigger. So that's the trivial part. So the other direction is now we want to show that if M is not a maximum, it's not a maximum matching, then there must be an augmenting path. Okay, so let's do that. Well, if M is not a maximum matching, well, then there must be some other matching, M star, which is maximum matching, which has strictly greater number of edges than M. Okay, so let's call that M star. So the size of M star is strictly larger than the size of M. So here's an example. Like going back to, this is not the same example. It's a different example. But let's say this is our graph. The blue edges are my matching. It's not the maximum matching. But there is a maximum matching, which like just pairs the vertices up like that. And that's M star. Now we're going to define the following set, S. So S is going to be the set of edges contained in M star or M, but not both. Okay? In other words, it's all the set of edges that are colored either red or blue, but not colored red and blue at the same time. So these matchings, I mean, in this particular case, they do not share an edge, but they could have. Okay? So if they do share an edge, I don't include that in my set S. But other edges, the purely red edges and the purely blue edges, they are in the set S. You can also write this as, it's M star union M minus their intersection. If an edge is in both of them, you don't consider it. Now, my goal is basically going to be to find an augmenting path in S with respect to M, right? With respect to the blue M. And here you can sort of see that it exists, right? So here's an augmenting path right there. But of course, this is one example. That doesn't prove anything. So we have to do this, argue about this more generally. But okay, so this is our set S. So what can we say about S? What observations can we make about the set S? Okay, so you can see in this graph now I eliminated that black edge, so it's now only red and blue edges. Well, what does S look like? Well, the first thing we can observe is that a vertex in S is incident to at most one edge in M star and one edge in M. Right? I mean, it cannot be incident to like two edges in M because, well, then M is not a matching. M will be a matching. Similarly for M star. So, in a sense, each vertex has degree at most 2, and if it does have degree 2, then one of those edges is blue and the other one is a red one. Well, if you have a set like this, and the set of vertices have degree at most 2, that means this set is a collection of cycles and paths. There's no other alternative here. And you can see, like, in this case, it is a collection, like the first, this red, blue thing at the top between 1, 2, 5, 6, that's like a cycle, an alternating cycle, and then you have a path in the bottom. It's a collection of cycles and path, and as we said, the edges have to alternate basically between red and blue. Okay, as we said, if you look at the vertex that's degree 2, then one of them has to be red, the other one has to be blue. Okay. So it's a collection of cycles and paths, and the edges alternate between red and blue. Now, one thing I know about S is that the number of red edges has to be more than the number of blue edges. Why? Because M star, as we said, as we assumed, is a bigger matching than M. Right? M, we said, is not a maximum matching. M star is a maximum matching. M star has strictly more edges. And when you take out, in S, when you take out the intersection of M and M star, it doesn't affect the fact that the number of red is going to be more than the number of blue. Okay. Now, the cycles, if we look at the cycles in S, they have to have an even length. So this is something actually that I think you're going to prove in the homework. Okay? Whenever you have a cycle in a bipartite graph, it has to be of even length. You can check it. It's true. It cannot have an odd length cycle. So cycles in bipartite graphs have actually even length. And that means that the number of red and the number of blue edges in these cycles are the same. But what does that mean? But we also know that the number of red has to be strictly more than the number of blue. So there must be some path in this set S which has strictly more red than blue. Well, that's an alternating path, and it has more red than blue, so I can augment. It's an augmenting path with respect to M, the blue edges. And in this case, the augmenting path is 3, 7, 4, 8. I can augment it, I can change it, I can make 3, 7 blue, 4, 7 not blue, and 4, 8 blue again. And that's your augmentation. So we saw that if M, this blue maximum, this matching M, if it's not maximum, we can always find an augmenting path. And as I said, this leads to an algorithm for finding a maximum matching. This is like you have to find an augmenting path with respect to M. So how do you do that? How do you find an augmenting path? So you can do it as follows. I'm going to do this. I have to do this quickly, but so here's your graph. What you do is, and this is your matching, the red edges. If an edge is in your matching M, you direct it from left to right. If it's not in the edge, you direct it from right to left. just like that. And then you can show, and this is an exercise for you, there is an augmenting path with respect to M, if and only if there's a path from an unmatched vertex on the left side to an unmatched vertex on the right side. So in this case, the paths would start from 4, go 4, 8, 2, 5, 1, 7. So that's your augmenting path. So this is an exercise for you to show. It's not hard to see this. And then basically, you know, after you've done that, you can basically do a DFS, depth first search, starting from an unmatched vertex on the left, do a DFS, and then see if you hit a node on the right that's unmatched. Once you do that, once you find that, that's an augmenting path, and you augment it. You do that, takes about order m times n time, and you can check that's true, and you're done. Okay, so that's it. So we talked about maximum matching, stable matching, very fundamental problems. And yeah, that's all I have to say for today.